Routing high current and high frequency power wiring requires careful consideration to ensure safety, efficiency, and electromagnetic compatibility. Here's a breakdown of key techniques to consider. Firstly, optimize cable size and separation. Increase cable size to reduce current density and minimize electromagnetic field emissions. This reduces heat generation and improves efficiency. Maintain adequate separation between cables to minimize inductive coupling and crosstalk. This prevents unwanted signal interference and ensures stable operation. Secondly, use shielding and grounding. Enclose the cables in shielded enclosures or conduit to minimize electromagnetic field radiation. This prevents interference with nearby equipment and reduces the risk of electromagnetic interference-related issues. Ground the enclosures and shields to prevent electrostatic discharge. This protects equipment from damage and ensures safety. Thirdly, isolate sensitive equipment. Locate sensitive electronic equipment as far away as possible from high current wiring. This minimizes the risk of interference and ensures proper operation. Use shielded cables or fiber optics to connect sensitive equipment to minimize interference. This provides an extra layer of protection and ensures reliable communication. Fourthly, choose appropriate cable materials. Use high temperature and fire-resistant cables to withstand the heat generated by high currents. This prevents damage to the cables and reduces the risk of fire. Consider using flexible cables or bus bars to accommodate movement and vibration. This prevents stress on the connections and ensures long-term reliability. Fifthly, implement electromagnetic compatibility mitigation techniques. Install filters, suppressors, and surge protectors to mitigate electromagnetic field emissions and protect sensitive equipment. This reduces the risk of interference and ensures proper operation. Use common mode chokes to reduce conducted emissions. This prevents noise from traveling along the power lines and interfering with other equipment. Sixthly, use fiberglass reinforced plastic cable trays or bus bars. Fiberglass reinforced plastic cable trays provide electrical insulation and minimize electromagnetic field radiation. This reduces the risk of interference and ensures safety. Flat bus bars offer excellent current carrying capacity and minimize voltage drop over longer distances. This improves efficiency and reduces heat generation. Seventhly, ensure proper bending and terminations. Avoid sharp bends in cables to prevent overheating and current restriction. This ensures proper current flow and prevents damage to the cables. Use proper cable terminations and connectors to ensure secure connections and minimize resistance. This prevents loose connections and reduces the risk of overheating. Eighthly, ensure adequate ventilation and cooling. Ensure adequate ventilation around high current wiring to dissipate heat and prevent overheating. This prevents damage to the cables and reduces the risk of fire. Consider using fan-cooled cable trays or enclosures to improve cooling. This is especially important in high current applications. Ninthly, perform regular testing and maintenance. Perform regular testing to verify wiring integrity, grounding, and insulation resistance. This ensures safety and prevents problems from developing. Inspect cables and connections periodically for signs of damage or wear. This allows you to identify and address problems before they become serious. Additional considerations include determining the specific frequency and current requirements of the application. This will help you select the appropriate cables and components. Consult with a qualified electrical engineer for detailed design and installation guidelines. This ensures that the installation is safe and compliant with all applicable codes and standards. Comply with relevant electrical codes and standards for safety and performance. This is essential for ensuring a safe and reliable installation. It is critical to select the appropriate cable size based on the current carrying capacity and ambient temperature. The National Electrical Code, or NEC, provides tables such as Table 310.15b16 that offer ampacity ratings for various conductor types and sizes under specific conditions. For example, a copper conductor THHN insulation rated for 90 degrees Celsius installed in a raceway may have a different ampacity rating compared to the same conductor installed in free air. Ampacity dating factors must be applied when multiple conductors are bundled together or when the ambient temperature exceeds the values specified in the NEC tables. These dating factors reduce the allowable current carrying capacity of the conductors to prevent overheating and insulation damage. Shielding is a critical aspect of high current, high frequency wiring to minimize electromagnetic interference. Shielded cables, conduits, and enclosures can significantly reduce the radiation of electromagnetic fields from the wiring, preventing interference with nearby electronic equipment. The effectiveness of shielding depends on the material used, the thickness of the shields, and the frequency of the signal. Copper and aluminum are commonly used shielding materials due to their high conductivity. Proper grounding is essential for safety and electromagnetic compatibility. Grounding provides a low impedance path for fault currents to return to the source, minimizing the risk of electric shock. It also helps to reduce noise and interference by providing a reference point for electrical signals. The grounding system should be designed in accordance with the NEC requirements, including the use of grounding electrodes, equipment grounding conductors, and bonding jumpers. The NEC provides specific requirements for grounding electrode systems in sections 250.50 through 250.70. These sections outline the types of grounding electrodes permitted, such as metal underground water pipes, ground rings, and concrete encased electrodes, and the requirements for their installation. Bonding jumpers are used to connect metallic parts of the electrical system together to ensure that they are at the same electrical potential. This minimizes the risk of electric shock and reduces noise and interference. The NEC specifies the size and installation requirements for bonding jumpers in section 250.102. Overcurrent protection devices, such as fuses and circuit breakers, are essential for protecting wiring and equipment from overloads and short circuits. These devices interrupt the flow of current when it exceeds a predetermined level, preventing damage to the wiring and equipment. The selection of overcurrent protection devices should be based on the ampacity of the conductors and the rating of the equipment being protected. The NEC provides guidelines for selecting and installing overcurrent protection devices in Article 240. Proper termination techniques are crucial for ensuring reliable and safe connections. Loose or corroded connections can cause overheating, voltage drop, and even fire hazards. Use appropriate connectors and tools to make secure and reliable connections. Torque connections to the manufacturer's specifications to ensure proper contact pressure. Inspect connections periodically for signs of corrosion or looseness and tighten or replace them as needed. Ventilation and cooling are essential for dissipating heat generated by high current wiring. Insufficient ventilation can cause the wiring to overheat, leading to insulation damage and reduced lifespan. Provide adequate ventilation around wiring and equipment to allow heat to dissipate. Consider using fan-cooled enclosures or cable trays to improve cooling in high-current applications. Select appropriate cable trays and supports to provide adequate support and separation for the wiring. Cable trays should be made of non-conductive materials such as fiberglass reinforced plastic to minimize electromagnetic interference. The cable tray should be sized to accommodate the cables without overcrowding, allowing for adequate ventilation and heat dissipation. Proper bending radii are essential for preventing damage to the cables and maintaining their electrical properties. Avoid sharp bends that can stress the conductors and insulation. Follow the manufacturer's recommendations for minimum bending radii. Support the cables properly to prevent sagging or strain on the terminations. Use cable ties or straps to secure the cables to the cable trays or supports. Avoid over-tightening the cable ties, which can damage the insulation. Conduct regular inspections and maintenance to ensure the continued reliability and safety of the wiring system. Inspect cables, connections, and equipment for signs of damage, corrosion, or looseness. Test the insulation resistance of the wiring to ensure that it is within acceptable limits. Grounding impedance testing can be done to make sure the ground is at the correct impedance. Perform infrared thermography to detect hot spots, which can indicate loose connections or overloaded circuits. Address any issues promptly to prevent them from escalating into more serious problems. In high-frequency applications, impedance matching is critical for minimizing signal reflections and maximizing power transfer. Mismatched impedance can cause signal reflections, which can degrade signal quality and reduce efficiency. Use impedance matching techniques, such as transformers or impedance matching networks, to ensure that the impedance of the wiring matches the impedance of the source and load. Transmission line effects become more significant at higher frequencies. The wiring can act as a transmission line, with characteristic impedance, inductance, and capacitance. These effects can cause signal reflections, attenuation, and distortion. Consider the transmission line effects when designing high-frequency wiring systems. Use terminated cables to minimize signal reflections. Terminated cables are equipped with resistors at the end of the cable that match the characteristic impedance of the cable. This absorbs the signal and prevents it from reflecting back to the source. Ferrite beads can be used to suppress high-frequency noise and interference. Ferrite beads are small, cylindrical components that are placed around the cable. They act as inductors, which block high-frequency signals but allow low-frequency signals to pass through. This can help to reduce noise and interference in sensitive electronic equipment. Fiber optic cables are immune to electromagnetic interference and can be used to transmit high-frequency signals over long distances. Fiber optic cables use light to transmit data, which is not affected by electromagnetic fields. They are ideal for applications where electromagnetic interference is a concern. Surge protection devices can protect wiring and equipment from voltage surges caused by lightning strikes or other transient events. Surge protection devices divert the surge current to ground, preventing it from damaging the wiring and equipment. Use surge protection devices at the service entrance and at sensitive electronic equipment. Harmonic distortion can cause overheating and damage to wiring and equipment. Harmonic distortion is caused by nonlinear loads such as electronic ballasts and variable frequency drives. These loads generate harmonic currents, which can overload the neutral conductor and cause overheating. Use harmonic filters to reduce harmonic distortion. Harmonic filters are designed to block harmonic currents and prevent them from flowing through the wiring system. Power factor correction can improve the efficiency of the electrical system and reduce energy costs. Low power factor can cause increased current flow, which can lead to overheating and voltage drop. Use power factor correction capacitors to improve the power factor. Power factor correction capacitors are designed to compensate for the inductive reactance of the load and improve the power factor. Use appropriate testing equipment to verify the performance of the wiring system. Multimeters can be used to measure voltage, current, and resistance. Oscilloscopes can be used to view waveforms and analyze signal quality. Spectrum analyzers can be used to measure the frequency content of signals. Network analyzers can be used to measure impedance and transmission line characteristics. Proper documentation is essential for maintaining the wiring system. Keep accurate records of cable types, sizes, and routing. Document the location of all connections and terminations. Keep a record of all tests and maintenance performed. Proper labeling is essential for identifying cables and equipment. Label all cables and equipment with clear and concise labels. Use durable labels that will withstand the environment. Follow a consistent labeling scheme to make it easy to identify cables and equipment. Compliance with electrical codes and standards is essential for ensuring safety and performance. Follow the requirements of the National Electrical Code, or NEC, and other applicable codes and standards. Obtain permits and inspections as required by local authorities. Consult with a qualified electrical engineer to ensure that the wiring system is designed and installed in accordance with all applicable codes and standards.